Hello. In this video we're going to figure out how to solve for a molecular structure given a molecular formula, an NMR, and an IR. So I'm not going to go into the nitty gritty of it. I hope your professor or your lab TA taught you a little something how to do these and like the background behind it and how the machines actually work. I'm just going to teach you how to solve for it, as you're going to find in some of your lab courses or in your just lecture courses as well. So what we're given here is C4H8O2. The first thing you always want to do is figure out your degrees of unsaturation. So the formula is 2 times the carbons plus 2 plus the nitrogens minus the hydrogens minus your halogens. The X here represents halogens. So those will be your fluorines, chlorines, bromines. Divide that all by 2, and that'll give you your degrees of unsaturation. So for our formula, we plug in 4 carbons, 8 hydrogens, divide that by 2, we'll get 1. If it ends up being a negative number, don't worry about it. Just take the positive integer of it, because all we want is that value. So that 1, what does that tell us? We can, in this molecule, we can have either 1 ring or 1 pi bond. The more numbers you have, so if you maybe have 4, you could have 3 pi bonds and a ring, and that ends up looking like a benzene ring. Anyway, so given that we have 1, when we look at our IR, look for something or some kind of functional group that could have a double bond in it, or a pi or a ring. So let's go check out our IR first. Our IR is good for telling us what functional groups there are within a given molecule. So for introductory organic chemistry courses, you will only look at things from the 1500 mark and up. Don't look at anything below that. This is called the fingerprint region, so don't even worry about it. Look for distinguishable peaks. So this one right here, so this is 15, 16, 17, 1750 here. This is usually a very strong and easy to recognize. It's going to be your carbonyl, so a carbon double bonded to an oxygen. So this kind of takes care of our degrees of unsaturation. So we know there's no ring. We can safely say that it's going to be a C double bonded to an O. Let's look at our other peaks that are above the 1500 mark. This is a C sp3 to an H. So don't worry too much about it. Those are very common peaks. Anything above here, no, we know there's going to be no alcohol functionality, or there's going to be no carboxylic acid functionality, because there's no big dipping circular round dip here. That will be an O to an H. There's also no nitrogen, so you're not going to see anything here either. There's no C sp2 H's. Those would be a little further up here. So it's safe to say that we know our carbonyl is going to be one of our groups here. So you can solve these problems roughly just knowing your NMR, but IR is a good place to start to get a visualization of what you're working towards. So now let's go to our NMR. After doing a lot of problems, you'll be able to solve these problems only using your NMR. IR will just be using for checking your work, but let's go through it step by step now. So over here on the right is upfield, and the left here is downfield. How you end up being downfield is you're next to something electronegative, something that's going to de-shield you. Kind of messes with the spin of the hydrogens. Your NMRs will tell you the environment that those hydrogens are in. Again, your hopefully professor goes over it in more detail. I'm just going to tell you how to solve these. Let's start upfield actually. So down here are your integration values. Hopefully they'll be given to you. If not, you'll need a ruler and you have to know how to go between peaks. Might do that in a different video. Most likely they're going to give it to you in these introductory courses, because when you're seeing these on a test, you'll be in the crunch time, won't have time to do all that. Anyways, here we go. So this is a triplet. So there's 1 peak, 2 peak, 3 peak, fairly symmetrical. And then we go to the next one. It's a singlet, 1 peak. Over here is a quartet, 1 peak, 2, 3, 4. Again, fairly symmetrical. Doesn't mean much now for this problem, but in other problems, symmetry of your peaks is a bigger deal. So we have 3 hydrogens here, and we know it's going to split to a triplet. So what your splitting pattern will tell you is what's next to it. So there's the number of hydrogens in similar environment plus 1 rule. So this tells us there's a carbon next to it that has 2 hydrogens attached to it, right? And that'll give you this pattern here. So we're going to go look over here, because we saw something with 2 hydrogens, and this splits to a quartet. So 1, 2, 3, 4. So we need something with 3 hydrogens plus 1. That'll give us our quartet. So it's safe to say that these two guys are right next to each other and most likely going to split each other. This one here, it's a singlet, so there's a carbon next to it with no hydrogens attached to it, or some electronegative atom it's attached to. Has 3 hydrogens as well. So now we can start plugging in our pieces. I did this earlier. So these are the puzzle pieces we just figured out together. So we have our CH3, that's good there, and this one's CH2 there. I put them next to each other because they look like they might go well together. And then the C over here, good. And then our carbonyl we found here, that's going to be here. That's our degree of unsaturation as well. So now let's connect the dots and see how we did. Alright. So, the beauty of NMR and IR is you can usually check your work. It makes it very nice during a test, so you know you're getting at least some points on this one. So let's go and check it now, right? So, we have, let's start with the carbons. We have 4 carbons. 1, 2, 3, 4. Cool, I'm going to show the carbon here. There we go. So 4 carbons there, and then we have 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Cool. 2 oxygens. 1. Oh, we messed up. So it doesn't show up in here, and it doesn't show up in here. So now it's up to us to figure out where it should be and what would make it align with what our data shows. So this 4 down here, the 2 hydrogen here, this carbon does not have enough in it to pull it down to this ppm down here. Neither does this one. So because we know this carbon here is being pulled downfield because of this carbonyl, it's safe to say that if we erased here and put that last oxygen in, that could be our solution. So let's hide hydrogens. Oops, did I mess that up? Ta-da! There we go. So now let's go check our work again. So 1, 2, 3, all our hydrogens are there. Now we have all our oxygens in there too. So this functional group here is called an ester. It will not show up in your NMR. I mean, it does when you figure out your deshielding and your downfield, but it will not show up in your IR. So a good thing we were checking this. So our degrees of saturation was 1, good to go. All our hydrogens, all our carbons are here. And lastly, to check with our NMR, this 3 should be a little bit downfield. So this our oxygen's kind of pulling it down. Good. This one here, super pulled down by this oxygen and this oxygen at the same time. Good. This one over here pulled down a little bit next to the carbonyl. This will be a singlet because there's an electronegative atom to it. This is also good. It's a quartet because nothing over here is going to split these hydrogens, only splitting from over here. Alright, I think that's it. If you have any questions, please leave them below. I'll get them as quick as I can. If there's another troubling concept you're having trouble with, feel free to leave it down there. I'll try to make a video on it, or just send me an email directly. I'll try to answer it if I can. Alright, thank you. Good luck.